All right, let's get right into it. Deep inside every single processor, every high-speed chip we use, there's a kind of memory that is just ridiculously fast. It's called SRAM, and it's pretty much the secret engine that keeps our digital world humming along. And this is the key, making it actually work is this constant, high-stakes balancing act for engineers.
I mean, really think about that for a second. When you tap on an app, the processor needs information right now. Not in a millisecond, we're talking nanoseconds. So how does it grab onto a single piece of data, a 1 or a 0, and hold it so tightly, but also be ready to change it in, well, less than the blink of an eye? That right there is the magic and the massive challenge of SRAM.
So, here's how we're going to break down the engineering behind all this. First, we'll cover the basics. What even is SRAM? Then we'll get into the constant battle to keep it stable. After that, we'll dive into the main conflict, this tug-of-war between reading and writing, then the whole puzzle of performance, and finally, we'll look at the hurdles that engineers are facing today.
Okay, so let's start at square one. At its very heart, SRAM is all about creating the perfect, absolutely lightning-fast switch.
You see, the S in SRAM stands for static, and honestly, that's its superpower. Unlike the main memory in your computer, DRAM, which needs to be refreshed thousands of times a second, an SRAM cell just holds on. It grabs its data, its 1 or its 0, and it holds it as long as the power is on. No refresh needed. It just sits there, perfectly stable.
So how does it pull that off? Well, it uses this clever little circuit called a bistable latch. The easiest way to think about it is to imagine two light switches that control each other. If one is on, it forces the other one to be off. And that off switch, in turn, tells the first one, hey, you stay on. It's this perfect, self-reinforcing loop. It's like a seesaw that can only ever rest in one of two positions, all the way up or all the way down. It can't get stuck in the middle. And that's your 1 and your 0. And just to give you some perspective, let's put it next to its more famous cousin, DRAM. That's the main RAM in your computer. You know, if DRAM is a marathoner, it's great at holding tons of data pretty cheaply, but it needs constant sips of water to keep going, then SRAM is the Olympic sprinter. It is unbelievably fast, powerful, and stable, but it's also really expensive. That's why you only use it for the most critical, high-speed jobs, like a processor's cache memory.
Okay, so this memory cell is designed to be super stable, to just hold its state. But the thing is, the inside of a microchip is a really noisy, chaotic place. And that brings us to the very first major engineering headache, making sure that a 1 always stays a 1.
The number one enemy of keeping data safe inside a chip is just electrical noise. These tiny, random spikes and dips in voltage are happening constantly. And if one of those noise spikes is just big enough, it can literally push our perfect little seesaw right over the edge, flipping a 1 to a 0. And just like that, your data is corrupted.
Because of this, engineers have a way to measure a cell's resilience. It's called the static noise margin, or SNM for short. The best analogy is to think of it like a moat around a castle. The wider and deeper that moat is, the harder it is for an enemy, the noise, to get across and flip the bit. So a high SNM means you've got a really stable, really reliable memory cell.
And this right here, this brings us to the absolute core of designing SRAM. It's this fundamental conflict, this paradox that shapes every single decision an engineer has to make.
Okay, so check this out. For a memory cell to be stable and reliable, it needs that high noise margin, right? It has to be strong to resist any accidental attempt to change it. But you also need to be able to write new data to it. And to do that, you have to be able to overpower it and force it to change its state. So how on earth can something be both immovable and easily movable at the exact same time?
Well, this is where the real genius comes in. Engineers solve this by basically tuning two key settings, almost like they're adjusting levers on a complex machine. The cell ratio is tuned to make the internal parts of the cell really strong, so they can hold their ground and not get flipped when you're just trying to read from them. But the pull-up ratio is tuned to make another part of the cell just weak enough that when a write signal comes along, it can easily overpower it and flip the state. It's a beautiful solution.
And this quote just nails it. It really is a tug-of-war. When you read from the cell, you're just kind of peeking at what's inside. So you need the cell itself to win that tug-of-war and stay put. But when you write to it, you need that external signal to come in with overwhelming force and win decisively, yanking the rope over and flipping the state. The designer's job is to rig this game perfectly, every single time, for billions and billions of cells. No pressure. But look, getting that read-write balance perfect is really only half the battle. You also have to make the whole thing incredibly fast and power efficient. And that brings us to the next big piece of the performance puzzle.
Yeah, speed is never free.
It always costs energy, and it costs it in two main ways. First, there's dynamic power. That's the energy you burn every single time you actually read or write a bit, the cost of doing business. But then there's the sneaky one, leakage power. These are tiny little trickles of electricity that leak out of the transistors even when they're just sitting there doing nothing. And with billions of cells, that tiny leaking faucet turns into a huge river of wasted energy real fast.
And what about speed itself? Now, don't get hung up on the equation on the screen. At its core, it's just telling us about a fight. On one side, you have capacitance, which you can think of as electrical drag or friction, slowing everything down. And on the other side, you have the drive current, which is the muscle, the power pushing the signal through. So to make things faster, you either have to reduce the drag or you have to crank up the muscle. But of course, both of those decisions have big consequences for the cell size and how much energy it uses. It's yet another trade-off.
Now here's the kicker. All of these challenges we've talked about, stability, the read-write dilemma, power, speed, they all get exponentially harder as we keep shrinking everything down to the microscopic sizes we use today.
Modern engineers are basically fighting a war on four fronts. First, as transistors get smaller, their natural defense against noise, that SNM moat we talked about, it gets shallower. Second, tiny unavoidable imperfections from the manufacturing process, things that didn't matter on bigger chips, can now be fatal flaws. Third, the transistors themselves literally wear out over time. They get weaker. And if all that wasn't enough to worry about, you've got the cosmic threat. A random particle of radiation from deep space can literally zap a memory cell and flip its value, creating what's called a soft error.
So really, when you look at a modern processor, what you're seeing is an absolute masterpiece of compromise. Every single one of those millions of tiny cache memory cells is the result of this incredibly delicate balancing act. It's a perfectly rigged tug-of-war between competing laws of physics, all just to give you that instantaneous performance we all take for granted.
And this leaves us with a really fascinating question to think about for the future. As we keep pushing the limits of physics, demanding even more power from even smaller and more efficient devices, you have to wonder, when does something have to give? What will it be? Will engineers be forced to sacrifice a little bit of that rock-solid stability to get more speed? Or will we have to accept slower performance just to keep our devices efficient and reliable? That balancing act is far from over.